everybody. Today we're going to talk about sync and network optionality. My name is B5. I use my internet handle when I'm at work. I use my meet space name, Brendan, when I'm at home. You can call me either. I work in a company called Number Zero. We are a distributed systems bunch of people, and we make an open source networking library that was lovely teed up, thank you very much, called IRO. And today I want to talk to you about three things. I want to talk to you about some observations about sync. Today, with the whole agentic thing happening, I now feel like it's fun to kind of apply that to stuff that isn't normally this. So pretend for this observations section that I'm your networking library talking to you about stuff that I've seen. We're networking people, we know how to move bytes. It's a sort of, there's some general things that we've seen as lots of people have built lots of different sync protocols on top of IRO. Then I want to talk to you about electrical sockets. We'll get to that. And some memes. So first observation we need to sort of get out of the way. Can sync be network optional? No, we are your networking package. We need to exist. It's very important. I think just to sort of tee this up, the network optional quote came from the Local-First set of principles, which there's two interpretations of that. Network optional being no network ever, and network optional being extreme latency. The extreme latency thing I think is far more interesting. The second observation is we are at a distributed systems conference. I know that sounds a little bit silly, but we're here, and I think it's really nice to be able to lean on some of that academia. When we come from the world of sync, or we talk about sync, we often think about building novel stuff. The academia can help us because we can, if you go back and read through some of these papers, you can pull up bits that will help you have kind of touchstones to lean upon. Some of my touchstones are, we can't actually have sync. It's not a possible thing. You can't get three processes to agree over a network that they are in a consistent state. That's not a thing you can have. We have a formal proof of that. It blows my mind. The best we can do is sort of proxy that. And I think that's a really fun sort of thing to give ourselves a bit of a pat on the back. We are genuinely cheating physics when we get this stuff right. Next one, hot take, centralization is faster, right? And this can be really hard to sort of swallow when you're the kind of person who's trying to design something that maybe doesn't have a single point of failure. But we have actual real good papers written about this that we can draw upon. And the reason I bring up some of this background in academia is sometimes people ask us, your networking library, to break physics. And this is sort of, it's not delightful to sort of get in this place. So we have this set of questions we ask when we first start working with people, which is okay, yes, we all want blazing. Okay, blazing is important. And these numbers I have pulled out of my butt. This is not real, but this is how we tend to think about it. And what I think is important here is not the discrete values. They will be different for you. But what we have found is when we start asking these amps and ohms questions of okay, how many writes and reads are you doing? How many, what's the maximum latency that you need to be able to tolerate before you consider a peer not valid, right? These questions help us see a couple of things at the same time because you can apply use cases to this. Hey, my system, the thing that I'm doing, I need to have less than 10 millisecond max latency time because I'm building a surgery room that is going to use a robot to operate on a human, and if you drop any packets, someone's going to die. Well, now you're in a very hard real-time sync scenario, and all of your other innovation budget on these other dimensions are gone, right? And what I think is also exciting about this is we can look at the other side of that, where a lot of these different sync algorithms sort of are meeting those use cases where they are and spending their innovation budgets in different places. And that can mean that a lot of these approaches where we all say sync are actually talking from different perspectives, right? Trying to solve different problems. You heard Carl talking about how to really deal with high transaction frequency, high write throughput, but really the concurrent edit frequency is a challenge, right? And so you can see where a bunch of these different approaches kind of often, if you lay it out in terms of amps and ohms and what you're trying to achieve, it gets a lot easier to see where two approaches to sync are talking past each other. So to that end, one approach does not fit all, and I think that's really exciting because it leaves lots of space to play and understand where you can design a sync algorithm that meets a specific use case. And that to me is way more fun and what means that this kind of thing will be interesting forever. But there are some things that I feel like I've observed. This maybe is the hot take, but I think that all pairwise sync algorithms that I have witnessed so far have two phases that are always present. There's always at least one moment where we're doing set reconciliation, where we're deciding which ends of the wire have what, and then an actual data transfer. And I think the easiest one to sort of or the sort of like, but wait a second, let's think about a classic use case of a browser, just fetching a web page. What's the set reconciliation algorithm when you are a client just fetching stuff? If you think about the HTML that gets fetched originally, all of the references to all of the assets that the browser must fetch is a set, right? And so you have this like very nice set reconciliation approach of the server decides that it is always right, it has the canonical set, and your job as the client is to fetch parts of it. And so we already have some like partial replication of that because you can lazily fetch stuff. You can do things based on what the user clicks, right? And you can see how this gets even more sophisticated when you see stuff like HTTP push come in, where someone says, oh, you've asked for this web page, you're gonna need this stuff. And so now we're doing, maybe the set isn't actually like formally, what do you have and what do I have? But there's always some portion of that before you do data transfer. And so it's like, hey, generally it's sort of, I always sort of, when looking at a new sync algorithm, ask like, hey, what are we talking about? Oh, I need that. Okay, a lot will add a third phase, which is incremental updates. That makes a lot of sense. Hey, we think we're generally in the same place. Let's just give bits and pieces that are the smallest delta on changes that are recent. That's a common approach. Here's the thing you need. But I think there's also something that we can pick up as an observation that we've seen a bunch is partial replication, CRDTs, and is this pattern that seems to be showing up in that sort of set reconciliation process is a recursive decomposition for more granular synchronization, where you can say like, hey, if you think about a CRDT and applying that to a graph structure of saying we're gonna give an identifier to every character in a document, we've really opened up the granularity of the space and we can now sync on much smaller things. But it has a downside, which is you have now a bigger sync state space, right? You have more items that you need to synchronize. And so there's this trade-off that gives you some really great properties where it's like, cool, we've blown it up just enough that we can sort of make certain problems go away. But we've now also created more stuff that needs to get synced. And where this really shows up is when you add authorization. Authorization really blows up the state space. And for us in the networking world, this generally usually translates down to who's even allowed to connect to whom about what. And every time we have sort of like finished something in the world of like public sync and then gone into, okay, now we just need to do this with authorization, all of a sudden the complexity just like explodes. So I'd heavily invite you to think carefully about authorization. This is my favorite observation of the whole thing. Clients and servers are both computers. And I know this feels like earth-shattering, but let's talk about what separates a client from server. There's three things. There's hardware, there's the dieability of it, and there are rules, right? This is it. This is kind of the distinction between a client and a server. Hardware being like, obviously, your server is in a rack somewhere, and it's amazing. And the hardware in a user's device is that awful Android phone from 1998, and that's just really bad. Dialability, the server is always publicly reachable, right? And we have this common pattern that we're always used to, which is just like, I'm going to dial from client to server because the server has this special characteristic of an IP that I can dial. And lastly, there are the rules. We, as developers, decide what a server is, what a client is, and we ship that software to those individual places. We at IRO work at number 0, working on IRO, work on the dialability part. For us, we think this is why we care about this stuff in the first place. The whole idea behind IRO and the big like thing is you should be dialing keys, not IPs. And this is kind of IRO's whole jam. If you look at, we've now gotten it down to basically one line. This constructs an endpoint, which under the hood will randomly generate a key pair, and you will have a public identifier of that. And at that point, anybody in the world can dial that. No matter where you are, if you are a client sitting with a phone in your pocket, if you are in a server, you're between two data centers, we don't care. There's a key that you can now dial. And that can go up into identity because it's a key pair for cryptography, and then go down into dialability. And with that taken care of, we can now sort of focus on hardware and roles. And I would posit to you that hardware is kind of like the terrain that we operate on. It's immutable landscape. So we don't need to worry too much about like, oh, we need to ship more hardware to people. That's kind of out of our hands. But the roles we can think about. And the roles brings me to electrical sockets. And this is a weird jump, but electrical sockets are super fascinating. And I'm sure you haven't spent much time thinking about them. But electrical sockets have this very interesting property that are all the plugs in this room, all of the plugs that you have encountered, at least in every region that has the same shape of plug, has a sublinear scaling characteristic, which means that as the number of plugs you have goes up, the amount of work each plug needs to do goes down. When we talk about peer-to-peer, this is the thing we want. This is the thing that gets us out of like, hey, this will work better when you're in high latency, into like, no, this is legitimately just a straight up physically better way to operate. Sublinear scaling is the thing that we care about, and it's why we care about peer-to-peer. Examples of sublinear networks, we have electrical grids. As you make a skyscraper, the size of a plug doesn't get bigger. As you have a cardiovascular system, is also a sublinear network. City roads are sublinear networks, right? But all sublinear networks have these three characteristics. They are always space filling. This one feels weird, but if you think about your arteries, it fills the space naturally. In networks designed for computers, we have to think about, hey, how do we make sure that we organize the topology of this network so that we're not stepping on each other's toes? We want to fill space, we don't want to collide so much. The sublinear network is fractal. And so it means that you can hierarchically apply a concept down, right? The same thing about your artery splitting, think about power boxes in buildings, sending less and less power over time. And this is the hardest part, they all have the same terminal units, which means that you can, at the very end of any of these things, you can take two ends and you can hot swap them, and they will behave the same. And this is the single hardest part about what we do, because that for us means client and server need to be node, which is difficult, easier said than done. So with that, I thought we would end with some memes, and I'm gonna show you some stuff live to sort of like try and put our money where our mouth is a little bit. This is going to be a demo. I'm going to ask for your participation. This is going to break because I coded this up, and our engineers have way more time. Ira works, but the janky code that I write doesn't always. And so what we're going to do is I'm going to first click. Oh, I'm going to get my GitHub out of the way. Okay. I'm going to do this, and then I'm going to ask all of you to go here. There's a QR. Carl asked me to make this QR code. If it doesn't work, I'm sorry. And what this is going to do is it's going to download 9 megabytes of WASM. I promised memes. I did not promise, what would I call this? I did not promise memes that are visual. But if the demo gods are good, oh, hey, what's up, everybody? All right, all right. So you are all in here. What we have done is we have taken all of this, we've compiled it to WASM, where hopefully we'll see some like graph movement in our metrics over here. But you now all inside of your browsers have a node. You have a piece of software that can survive and is resilient and knows how to contact other things. There's an endpoint running in there, and you're all talking to each other and synchronizing. I can write some memes. Okay, cool. We'll see how we do. And hopefully we'll see some like actual traffic show up here. But this is kind of the idea. Like, this is real, it works. This goes even faster if we can do it natively, but this is the core principle that we think is like, yeah, peer-to-peer for the longest time has been plagued by like a lot of really low-level details of NAT traversal, of how do you get this thing to function. And hopefully you can see here that the value is like, no, this actually is doable. We can have this in open source library today. And if you bear with me, I'm going to do one thing that is going to feel weird. I am going to, the server that is running this is actually running on my computer right now on the stage. And so I'm going to turn it off. So that's it. And we're going to say no more to you. Now, if you're still on that web page and you add more, can somebody see if you can get this? If you refresh it, it'll die. But see if we can actually get this to... Did it work? It's not working for me, but it's worth a shot. Some of you should see actual updates where you're actually connected to each other, because this thing is not critically centrally reliant. Everything else is working. But yeah, that's kind of what I had. If you have any other questions, that's kind of it.
A couple of minutes for questions while the next speaker gets set up. All right, got one already.
Real quick, what was the paper on why centralized is sometimes good? What was the title again?
On the value of even a little centralization in distributed systems, I think is the one. You have to spend a lot of time learning about Poisson clocks, which is a lot. But if you spend time with the paper, I left it believing in like, oh, okay, centralized is just going to be faster.
I'm curious how you think about like the long term of reachability, especially for like NAT and hole punching and all that. It's just there's a very long tail of network types to support, and yeah, like at what percent do you stop caring?
Yeah, we would, I mean, we'll never stop caring is the is the short answer. We've been working very heavily towards IRO 1.0, and for that, IRO is the Quick API under the hood, and we think that Quick Multipath, which is an extension on Quick, can actually be turned into Quick Multi-Transport. And so our plan is just to kind of go through WebRTC, Wi-Fi aware, Bluetooth Low Energy, and like all of these, and have those all be things that IRO can be made aware of and make use of. And so the thing about networking that is funny is it's more lore than spec. Like right now, we've been spending more time like debugging why Asia Pacific South behaves so differently because they have carrier grade NATs, and so like it just never goes away.
All right, let's give a hand of applause for Brandon.